My name is Markus Wallinger and I'm presenting Faster Edge Path Bundling through Graph Spanners. This was joint work with Daniel Archambault, David Auber, Martin Nöllenburg and Jaakko Peltonen. Edge bundling techniques reduce the clutter in trailsets or drawings of graphs by visually clustering similar edges. Similarity between edges is usually defined on attributes such as length, proximity or angle between edges. The difference between trailsets and in drawings of graphs lies mainly in what information is available. In trailsets, edges usually only have a start and an end location, for example the trajectories of cars traveling between cities, while in drawings of graphs there's also the connectivity information from the graph itself available as information on top. In the related work we can mainly differentiate between structure-based and image-based approaches. In structure-based approaches, such as force-directed bundling, the similarity of edges is computed on structural information of the instance itself. In image-based approaches, such as Kubo, the similarity between edges is computed on the pixel information of individual edges. Worth mentioning here are also conjoint drawings, where edges should be drawn similar to train tracks. However, this constrains the problem too much and they mainly remain the theoretical concept. However, there exist some heuristic approaches, but they require that the layout of the graph is computed as well. Edge path bundling is inspired by the conjoint drawing and structure-based approaches. Here, edges are not bundled by pairwise similarity, but rather edges are bundled against an existing path in the graph. Let me briefly reiterate the edge path bundling algorithm on a small example. First, we sort the edges descending by the edge length. Next, we compute new edge weights by raising the edge length to the power of a weight factor kappa. This makes it possible to later prefer short edges in a shortest path. Now, for each edge, we remove the edge from the graph and compute the shortest path between the endpoints. If the length of the path is less times t, the edge length, we bundle the edge against the shortest path. We repeat steps 3 to 5 until all edges are either bundled or used as a support. Now, a graph visualization is considered faithful if the underlying network data and the visual representation are logically consistent. Most bundling approaches, however, do not differentiate between trailsets and graphs. The independent edge ambiguity is not a problem when bundling trailsets. For example, UV and XY are in close proximity, have a similar angle and length, and therefore should be bundled. However, for graphs this is problematic, because there's a connection implied between x and v and u and y, which is not present in the underlying data. On a global level, if we look at 500 unconnected edges that are randomly placed in the plane, the noise becomes signal. However, edge path bundling does avoid those independent edge ambiguities by bundling edges against existing paths in the graph. A major limitation of edge path bundling is that it is rather slow when compared against other state-of-the-art bundling approaches. This is mainly caused by the fact that we repeatedly perform a Dijkstra's shortest path computation for each edge in the graph. Therefore, the performance of edge path bundling is mainly bounded by the number of edges in the graph. The main motivation of this work was to improve the performance of edge path bundling while delivering a similar visual quality for the bundling itself. We made several observations that guided this work. For example, some vertices and edges are explored but can never be considered on a bundling path. Take the edge between u and v in the example on the right. If we remove it and try to compute a shortest path between u and v, we will probably start at u, explore the component, and then terminate without finding a path. Similarly, we might end up in vertices such as t that are explored but can never contribute to a bundling path. Therefore, we should ignore vertices and edges that are not needed for path bundling. Another observation was that short edges are usually used in a bundling path. That means if we take, for example, the red edges, they are more likely to be a support of another edge's bundling path than that they are bundled themselves. And also, we had another observation that computing an edge path bundling is similar to computing a greedy graph spanner. Therefore, we thought it should be possible to compute a path bundling on a sparse subgraph. Let's take a closer look at observation 1 and how the problem size can be reduced. Remember, some vertices and edges are explored but can never be considered on a bundling path. The example here shows the drawing of a graph and its edge path bundling. What you can immediately notice is the edge between U and V can only be bundled if there would be a second edge between the left subgraph and the right subgraph. This is very similar to a biconnected component in graph theory. Therefore, we can perform a biconnected component decomposition. Now, to compute the bundle, we just bundle the components individually and construct the graph back together from the individual components. One computational advantage this also has is that we can bundle the components in parallel. In the first experiment, we compared the effects of the biconnected component decomposition on 5 real-world datasets. The first observation that can be made is that the number of components is rather large when compared against the number of vertices. However, the number of components of size bigger than 2 in terms of number of vertices is relatively small. This means we only have to bundle a limited number of subgraphs. Also, if you look at the size of the largest component in terms of vertices, you can see that it also already drastically reduces the size of the graph. Now, when looking at the runtime of edge path bundling and edge path bundling with the biconnected component decomposition, we can make 2 observations. The smaller datasets profit from the biconnected component decomposition, and in all instances the runtime was reduced. However, it seems like that they don't gain that much, mainly because of the overhead of performing a biconnected component decomposition and computing the subgraphs. Now, for the larger datasets, however, it drastically improved the runtime. If you look at the Panama papers with 700,000 vertices and more than 1 million edges, it improved the runtime from 11.5 hours to 1 hour and 80. Let's come back to the other observations we stated and let's focus on the similarity to graph spanners. So, in this context, when we talk about graph spanners, we mean multiplicative T-spanners. A multiplicative T-spanner of a graph G is a subgraph with the same vertex set. However, the edge set only contains edges where there's no alternative path that is T times the edge length available. Now, how to compute the greedy T-spanner? We start off by sorting the edges ascending by the edge weight. This is similar to edge path bundling, where we sort the edges by descending edge length. Then we create an empty graph with the same vertex set, but initialize the edge set as empty. Then for each edge according to the sort order, we compute the shortest path between source and target. Now, if the path is longer than the T times the edge weight, we add the edge to the edge set. We repeat this process and will eventually arrive at a greedy T-spanner. In this example, you see the migrations dataset with approximately 7,000 edges. At the bottom, you see only the spanner edges visualized. In this case, it is a T-spanner with a value of T equals to 2. That means each red edge that you see guarantees us that each edge that is not in the spanner has at least a path that is at most twice the edge length. What you can immediately notice is that this graph is much sparser and therefore should speed up the Dijkstra computation massively. Now let's take a look at the spanner edge path bundling algorithm that ties together the observations we had on spanners and the original edge path bundling algorithm. Essentially, the input compared to the edge path bundling algorithm stays the same. We still need a graph, its drawing, a weight factor and a distortion factor, and the output are control points for path bundling. However, it is a bit different. For the spanner edge path bundling algorithm, we start off by computing a multiplicative T-spanner on the graph and its drawing. You can take a look at the running example, and this is exactly the spanner for this example. Now, for all the edges in the spanner, we raise the edge weight or the length by our weight factor kappa again, with the same thought process as for the normal edge path bundling algorithm, that we want to prefer shorter edges on our paths, and this can be determined with the weight factor. Now, instead of computing the shortest path on the full graph G, we compute the shortest path on the graph spanner H, and we do this repeatedly for each edge that are not part of the spanner edge set. Let's come back to the example we saw earlier of the migrations data set. At the bottom, you still see the multiplicative t-spanner of the instance, with a distortion value of t equal to 2. Now, how does it look with the new spanner edge path bundling algorithm? What you can immediately see is that edges are bundled along paths in the spanner. Let me go back and forth once more to make it a bit more clear. Let's also take a look of the visual differences between the normal edge path bundling algorithm and the new spanner edge path bundling algorithms. At the top, you see the directed migrations dataset bundled with the edge path bundling algorithm. At the bottom, the same dataset is bundled with the spanner edge path bundling algorithm. Now, it's really hard to see any visual differences, so let me point out a few. In the center of the United States, you can see that this huge brown bundle is slightly different in the spanner edge path bundling algorithm. Similarly, in the Atlanta area, the bundles also behave slightly different, but there's no major difference in both bundling algorithms. And we also computed the quality metrics that on both data sets, and they confirm the visual similarity. We couldn't find any major differences in the quality metrics. Lastly, let's discuss the impact of parameter choice on the visual attributes of a spanner edge path bundling algorithm. Remember, the distortion value t determines the maximum length of a path an edge can be bundled against, while the weight factor kappa gives short edges preferential treatments when computing the shortest path in the spanner. Now, we increased t from 1.5 to 2 to 2.5 from top to bottom, while we increased the weight factor kappa from 1 to 2 to 3 from left to right. But you can immediately see with decreasing t, more edges are available in the spanner to be used as paths, splitting the drawing into more bundles. With increasing k, fewer edges are bundled because the threshold is harder to exceed. Shorter edges are favored for paths to be used in the bundling. Now, from a quality metric perspective, we would recommend using a distortion value of 2 and a weight factor of 2, as it was shown that this had the best overall performance regarding the quality metrics. In a computational experiment, we measured the runtime required to compute the bundling and compared edge path bundling against the new spanner edge path bundling algorithm. Although we have several variants of spanner edge path bundling implemented, in the presentation we will only compare against the best performance. For the rest, please see the paper. Now, in a comparison of the original edge path bundling algorithm, the ones we started out with at the beginning of our experiment, of our investigation, and the best performing spanner edge path bundling algorithm, you can see that the runtime to compute the bundling is drastically increased. Even more impressive is the behavior on the large datasets. Remember, the Panama Papers dataset has about 700,000 vertices and over 1 million edges. Before that, it required nearly 12 hours to compute the bundling. With the new approach, this can be done in under 10 minutes. In total, we could increase the runtime of the normal edge path bundling algorithms approximately 5 to 256 times, and we are now able to also compute the bundling on large graphs in a reasonable time. Compared to other bundling approaches, we can report that spanner edge path bundling is faster than most other approaches. Here, for example, winding roads or force-directed bundling. However, image-based approaches are still much faster. For example, Kubu requires only a few milliseconds to compute the Panama Papers dataset, and this is not depending on the number of edges, but just on the number of pixels in the image. To conclude the talk, we have shown a new variant of edge path bundling called spanner edge path bundling. Spanner edge path bundling is still a relatively simple algorithm. Computing a greedy spanner is not that much different of computing an original edge path bundling. However, spanner edge path bundling, including the biconnected component decomposition, is 5 to 256 times faster than normal edge path bundling. And visually and quantitatively, there are nearly no differences between spanner edge path bundling and edge path bundling. However, there are still some limitations with this work. Namely, ambiguities are avoided but can still be present. For example, if two unconnected components are in close proximity, their bundling might indicate that both components have a connection which is not present in the data, and therefore the drawing is not faithful. Similarly, shallow angle crossings are not necessarily avoided by spanner edge path bundling and can indicate an unfaithful representation of the data. Lastly, we are bundling against shortest paths. While paths usually have meaning, here they are mainly used as a tool to compute a bundling. Thank you for your attention.